Alright, hey, I'm calling these videos Are Real Numbers Real? But that's not necessarily the point of this, but just some thinking I've been doing about real numbers and some explorations of them that I thought I would share. There's a lot of different kinds of numbers. If you've worked in computer science or mathematics, you've certainly encountered things like integers, natural numbers, negative integers, rational and irrational, real numbers, transcendental numbers, complex numbers. There's a lot of different numbers. Real numbers are the ones that, are called real. They're presumably the ones that somehow actually exist. And, a real number is, 2.5, 3.67, pi, those kinds of things. And they seem to be, you measure the distance between two objects. It's not necessarily an integer. It's probably not a complex number. It's a real number. But I'm curious if that's actually an accurate representation of what these real numbers are. So I wanted to explore this, and I want to start with the idea of a natural number. And natural numbers are presumably something associated with nature, something that we associate with the natural world. And these are sometimes thought of as counting numbers. And how do you count things? You are in the woods and there's a pack of wolves coming at you and you want to know how many wolves there are. 1, 2, 3, there's 3 wolves. Here comes another one, now there's 4. Maybe they go away and there's 0. So the natural numbers are certainly things like 1, 2, 3, 4. And sometimes they include 0, depending on who you're talking to. We may or may not include those, but mostly they're the numbers we use to count things. So sort of the naturally occurring numbers. And numbers like, 2.5 don't kind of come up at first when you're thinking about how many wolves are chasing me through the woods. It's 2 or it's 3. It's not 2.5, right? These natural numbers, we can just, for now, assume they start from 1, 1, 2, 3, 4. They go on and on forever. So that's the first concept. And we have a funny little symbol we use to represent the natural numbers. It's the letter N with an extra bar on the left there. That means the set of all natural numbers. And so if we wanted to list everything that was in that set, it would be the elements 1, 2, 3, 4, 5, 6, and so on. So this brings up the question of how large is this set of natural numbers? How many things are in this collection? And we can think about a set. Consider a set which contains, I don't know, a happy face, a sad face, and a neutral face. So how many things are in this set? 1, 2, 3 things. And so we can say S with these bars on the side means the size of the set S. And in this case, the size of this set is 3. And we might make another set, T, which consists of the letters A, B, C. And if we ask for the size of T, that would be 1, 2, 3. So this thing with the little bars on either side of a set, a collection of things, that's just how big it is, how many things are in the set. But this raises the question, what's the size of this set of natural numbers? Well, we know it's bigger than 4 because I've already listed 6 elements here. Maybe it's 6, but probably not because, I could also list 7, and there's at least 7 things in this set. And you may be tempted to say the size is infinity, but that's not a number. And when we say, what's the size of this set, we're asking, what's the number of things in this set? And this symbol is not a number. What this means is bigger than any number. It's not a number itself. It's a way of representing something that is bigger than any number. So it's different from just a really large number. A billion is a really big number, but it's not bigger than 2 billion, right? So a billion is not the same as infinity. The diameter of the universe is a really big number. It's like 13 billion light years, but it's not bigger than any number. It's smaller than 14 billion light years. But this symbol infinity means something bigger than any number. And we can say, you know, the size of this is infinite, meaning it's bigger than any number. The number of things in this set is bigger than 10. It's bigger than 100. It's bigger than 1,000. It's bigger than a billion. Any number you think of, there's more than that number in this set. So this is an infinite set, but we wouldn't actually say the size is infinity, because infinity is not a number. It's a description of something being so big that it's bigger than any number. But we do come up with a special symbol for the size of the natural numbers, and that's something we call aleph naught. So it's a cool looking Hebrew letter if it's drawn correctly. This is not really the correct way to draw it, but this is just a symbol that means the size of this infinite set, right? It's not a number. It's not some number we can write out. It's something that's bigger than every number. Okay, so the size of the naturals is aleph naught. But there's another way we can talk about the size of a set. Think about our set S here. We said the size of it was 3. And our set T, we said the size of it was 3. So these definitely have the same size as each other. But there's another way we could determine that these two sets have the same size, even if we don't know that the size of this is 3 and the size of that is 3. The way we can know these have the same size is that we could make a one-to-one correspondence between elements in S and elements in T. We can say the happy face goes with A, the sad face goes with B, the neutral face goes with C. And every element of S goes to something in T, and every element in T goes to something in S. And it's one-to-one. We don't have two things going to A, we don't have two things going to the sad face, and so on. Since we can map each thing here to one thing here and vice versa, that tells us these two sets have the same size. And so even without knowing what the size of S and T are, we could say they have the same size. So this gives us the possibility of seeing things that have the same size as the set of naturals. So what does this mean? Well, the natural numbers consists of 1, 2, 3, 4, 5, 6, 7, and so on. Well, there's another set, which is the set of all integers. And integers are whole numbers plus 0 plus negative whole numbers. So, and we draw a funny looking Z with a double line on there. And the integers include 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and so on. Okay, this is also an infinite set. The question is, how does the size of this compare to the size of that? And it turns out they have exactly the same size. And the reason they have the same size is because we can make this one-to-one correspondence between the natural numbers and the set of all integers. And we can do this correspondence in the way that each number here gives us a number down here, and each number down here gives us a number there. And since we have that one-to-one correspondence, we can say the size of the set of integers is the same as the size of the set of natural numbers, which we said we're calling aleph naught. And so this is where where infinite sets start to get a little strange, because, you know, it clearly looks like there's a lot more stuff down here than there is up here. In particular, 1, 2, 3, 4, 1, 2, 3, 4, right? Everything that's in here is down here in the integers also, but there's all this other stuff. There's a 0 and there's all these negative numbers. In fact, there's an infinite amount of other stuff. There's all the negatives, but despite that, these two sets have the same size. So that's counterintuitive, right? If you have a set and you start adding things to it, you should end up with something that has more stuff in it. But under this idea of having a 1-1 correspondence, the number of things in here and here are the same. They're both aleph naught. This is another sense in which this is not a number. And you know, this doesn't work with finite sets. If I add the letter D over here, this is going to be a bigger set than that, because there's nothing I can map D to over here. All my faces are already mapped to. Unless I add another face over here. So by adding one thing here, this set gets bigger. But in the infinite case, by adding one thing here like a 0, the set doesn't get any bigger. And in fact, adding an infinite number of things here, the set still doesn't get any bigger. Okay, so the integers and the natural numbers, same size. All right, now remember I said sometimes we call the naturals our counting numbers. And this is another way to look at the fact that the integers have the same size as the naturals, because I can put them in an order where I can identify the first, second, third, fourth, fifth, sixth, seventh of these integers. And anytime I can do that, we say that the set is countable and countable means that I can put it in this 1-to-1 correspondence with the naturals. I can identify a first, second, third, fourth, fifth, and so on. And so any set that's countable is going to have the same size as the natural numbers, which is aleph naught. So now we can ask something like fractions between 0 and 1. So let F be the set of all fractions between 0 and 1. So a fraction is, you know, something like A over B. And there's a whole lot of fractions that I can write as A over B. I can write 1/2, I can write 3/5, I can write 17 over 85, I can write 1,426 over 85,219. Those are all fractions. And there's certainly an infinite number of fractions I can write like this between 0 and 1. Just means the top number is smaller than the bottom. And it's almost like there's an infinite number of these, right? Because I have an infinite number of choices for the bottom. And for each of those, you know, I can write any number up to that on the top. I could write 10 billion over 10 billion and 1 and get a new fraction. But it turns out I can arrange these fractions in a way that lets me say, here's the first one, the second, the third, the fourth, the fifth, and so on. So here's what I'm going to do. I'm going to start with 1 over 2, and I'm going to do 1/3 and 2/3. Then I'm going to do 1/4, 2/4, 3/4, and then I'm going to do 1/5, 2/5, 3/5, 4/5, and then 1/6, and so on. And I'm going to say this is the first, this is the second, this is the third, the fourth. Now if I want, I can eliminate duplicates. I've already got 1/2 here, so I could skip this, and I could say this is the fifth, this is the sixth, the seventh, the eighth, the ninth, the 10th, and so on. And again, I've got a 1-to-1 correspondence between the natural numbers and all the fractions, right? Any fraction that I come up with will eventually appear in here and will correspond to one integer. And so the size of this set of fractions is also going to be aleph naught. Okay, so that's the first part of this, right? This idea that Natural numbers, there are counting numbers. There's an infinite number of them. We have a symbol that says how big they are. But there's lots of other sets that seem like they should be bigger but are actually the same size, according to this definition, are actually the same size as the natural numbers. And anytime we can count things and say here's the first, second, third, fourth, fifth, and so on, we have something with that same size, which we call aleph naught. So when we go on to real numbers, this is where things start to get a little strange.